Welcome to The Explainer. Today, we're going to crack one of chemistry's biggest codes, the ultimate showdown between metals and nonmetals. I mean, it seems like a pretty simple question, right? But really think about it for a second. You've got two pure elements, but they are worlds apart. One's shiny, it's strong. The other, brittle and dull. So what's the real secret here? That's what we're doing today. We're going to play chemical detective and find the one big clue that explains everything. Okay, so let's introduce our two main groups of suspects. In one corner, you've got the metals, things like iron, copper, gold. And in the other corner, the nonmetals, like the carbon that makes up charcoal, or even the oxygen in the air. I mean, they're literally everywhere, but they play by completely different rules. So let's start gathering some evidence, shall we? Any good detective starts with the obvious stuff, right? So we're going to start with the physical clues. What do they look like? How do they feel? What happens if you, say, hit them with a hammer? It's time to gather the forensics. Okay, first piece of evidence, luster. And yeah, that's really just a fancy way of saying shine. If you take a pure metal and polish it, it just gleams, reflecting light like crazy. Nonmetals, though? Nah, they're usually pretty dull. They just don't have that sparkle. All right, next up, malleability. In other words, can it take a beating? And for metals, the answer is a big yes. You can hammer them flat into these super thin sheets and they won't shatter. Gold and silver are the absolute masters of this. You can pound them into gold leaf so thin it's practically see-through. Now, try doing that with, say, a chunk of sulfur. You're just going to end up with a pile of dust. And right alongside that is something called ductility, which is just the ability to be pulled out into a thin wire. This is where metals really show off. And get this, a single gram of gold, just one tiny gram, can be stretched into a wire that's 2 kilometers long. I mean, that is just incredible. So let's quickly recap the evidence we've got. Metals, generally hard. They're amazing at conducting heat and electricity. That's why all your cooking pots and electrical wires are made of metal, right? And they're sonorous, which means they make that nice ringing sound when you strike them. Nonmetals, on the other hand, are basically the total opposite in every way. Seems pretty open and shut, doesn't it? Well, not so fast. Because this is where our simple little case gets a massive plot twist. Let me introduce you to the rule breakers. You've got mercury, a metal that's actually a liquid at room temperature. Then there's gallium, another metal that will literally melt in the palm of your hand. And it goes the other way too. Graphite, which is just a form of carbon, a non-metal, it conducts electricity. And iodine, another non-metal, is actually shiny. See? All these exceptions prove that just looking at the physical clues, well, it's just not going to be enough to crack this case. So, if the physical evidence is misleading, we've got to go deeper, right? We need to look at something more reliable, and that's where the chemical fingerprint comes in. We're going to see exactly how our suspects behave when we put them under a little pressure, starting with how they react with something as simple as the air around us. Okay, so when a metal meets oxygen, you've all seen iron rust. That's exactly what's happening. It forms what we call a metal oxide. Now, for the most part, these oxides are basic. That just means if you dissolve them in water, you get an alkaline solution, basically the chemical opposite of an acid. But, and this is the really important part, not all metals react with the same amount of, let's say, enthusiasm. And this is where a really clear hierarchy starts to appear. I mean, at one extreme, you have stuff like sodium and potassium. These guys react so violently with air that you actually have to store them in oil just to keep them safe. Then, on the complete other end of the spectrum, you have gold and silver. They're so unreactive, you could leave them out for thousands of years and they wouldn't tarnish. It's exactly why gold is so prized for jewelry and in important electronics. It just lasts. Now this is a much better clue. All right, so we've seen how they handle air. What about water? What happens if we add that to the mix? Well, as you can probably guess by now, the reactions are all over the place, and they tell us even more about the true nature of these elements. And yeah, a very clear pattern starts to emerge. Sodium, it practically explodes in cold water. Magnesium is a little pickier. It'll only react with hot water. And then there's iron, which is even more stubborn. It won't do a thing unless you blast it with steam. So this really starts to confirm that pecking order we were talking about. Okay, so after seeing how they behave with air and water, we've got enough evidence now we can finally arrange our suspects into a proper lineup. This is the official pecking order. And the final piece of evidence that locks this all in place is something called a displacement reaction. It's actually pretty simple. A more reactive metal can literally push out or displace a less reactive metal from its compound. Think of it like a power struggle. The stronger, more reactive metal is always going to win. And all of this evidence, all these reactions, they lead us to the grand reveal, the reactivity series. This is it, the definitive ranking. You've got the most aggressive reactive metals, like potassium, right at the top, and the list goes all the way down to the totally chill, unbothered metals like gold at the very, very bottom. This series right here, this is the key to the whole thing. So we figured out how they all behave. But, our detective story isn't over yet. We're still missing the most critical piece of the puzzle, the motive. Why? Why are some metals so desperate to react while others just don't care? The answer, it turns out, lies in something totally invisible. So here's the absolute heart of the matter. Every single atom in the universe wants one thing above all else: stability. They all want to be like the cool kids on the block, the noble gases, neon, argon. And those gases are perfectly stable. Why? Because their outermost shell of electrons is completely full. And that drive, that need to have a full outer shell, well, that's the motive behind everything in chemistry. And this is where it all clicks into place. Metals are givers. They've got just 1, 2, or maybe 3 extra electrons in that outer shell. Think of those electrons like an extra piece of luggage they are just dying to get rid of. By giving away those few extra electrons, they expose the next shell down, which is already full and stable. And boom, they're happy. Nonmetals, as you might guess, are the complete opposite. They are takers. They're hanging out on the right side of the periodic table, and they are so close to having a full outer shell. They're just missing 1 or 2 electrons to be perfect. So you can imagine, when they see a metal that's desperate to give some electrons away, they are more than happy to take them. And this setup creates the perfect exchange. The classic example is making table salt. So you've got sodium, a metal, with 1 electron it wants to ditch. Then you've got chlorine, a nonmetal, that needs just 1 more electron to be complete. It's a perfect match. Sodium gives its electrons to chlorine. When that happens, they both become charged particles called ions. Sodium becomes positive, chlorine becomes negative. And what do opposites do? They attract. They stick together like super strong magnets, and presto, you have sodium chloride, or what we just call table salt. And really, that's it. That is the solution to our whole mystery. That simple little dance, the giving and taking of electrons, that is the fundamental reason for everything we've looked at. It explains why metals are shiny, why they're strong, and even why some of them literally explode in water. In the end, it all comes down to the electrons. So that leaves us with one last thought, doesn't it? If this basic exchange of electrons can create something as common and essential as salt, just imagine what other incredible compounds are out there, waiting to be created. What happens when you pair up the most reactive givers with the most eager takers? The possibilities? Well, they're quite literally explosive.
Thank you for watching CBSE One Shot. If it helped you, like, share and subscribe.